Hello friends, thank you for watching this video. So before I will start with this topic, the dining philosopher's problem, first it is important for us to know its definition. The operating system is a program that links the user and the computer system. This operating system must be capable of controlling resource usage. In the process of designing the operating system, there is a common foundation called concurrency. Concurrent processes are when the processes work at the same time. This is called the multitasking operating system. Concurrent processes can be completely independent of the other, but can also interact with each other. Processes that require synchronization to interact properly controlled. However, the concurrent processes that interact, there are some problems to be solved such as deadlock and synchronization. One of the classic problems that can illustrate the problem is the dining philosopher's problem. The dining philosopher's problem can be illustrated as 5 philosophers who would eat. On the table was reserved 5 chopsticks. If philosophers are really hungry, then it will take 2 chopsticks, which is in the right and left hands. However, sometimes only one course takes chopsticks. If there are philosophers who would take 2 chopsticks, then there are philosophers who will have to wait until the chopsticks are placed back. Inside this problem, there is the possibility of deadlock, a condition in which 2 or more processes cannot continue execution. So what is the dining philosopher's problem? In computer science, a dining philosopher's problem is an example problem often used in a concurrent algorithm designed to illustrate synchronization issues and techniques for resolving them. It was originally formulated in 1965 by Edsger Dijkstra as a student exam exercise, presented in terms of computers competing for access to tape drive peripherals. Soon after, Tony Hoare gave the problem its present formulation. The dining philosopher's problem states that 5 philosophers seated around a circular table. There is 1 chopstick between each philosopher. A philosopher may eat if he can pick up the 2 chopsticks adjacent to him. 1 chopstick may be picked up by any of its adjacent followers, but not both. The problem was designed to illustrate the challenges of avoiding deadlock, which means a system state in which no progress is possible. To see that a proper solution to this problem is not obvious, consider a proposal in which each philosopher is instructed to behave as follows. First, think until the left fork is available. When it is available, pick it up. Second, think until the right fork is available. When it is available, pick it up. When both forks are held, eat for a fixed amount of time. Then put the right fork down, then put the left fork down, and repeat from the beginning. The philosophers have now the chance to not get starved to their eat. If one philosophers are hungry, let him eat. This attempted solution fails because it allows the system to reach a deadlock state in which no progress is possible. This is a state in which each philosopher has picked up the fork to the left and is waiting for the fork to the right to become available. With the given instructions, this state can be reached, and when it is reached, each philosopher will eternally wait for another, the one to the right, to release a fork. If one philosopher drops his fork, the other one philosopher will get the fork and eat the bowl. The dining philosopher's problem solution. Now let's see how this dining philosopher's problem works using a semaphore. By using a semaphore, or a numbering in common term, To represent the chopstick, it can be picked by executing a wait operation on the semaphore and released by executing a signal semaphore. The structure of the chopstick is shown below. Assume that we have a semaphore array chopstick of 5. The structure of a random philosopher I is given. In this portion, we have a code fragment of the do-while loop that represents how is this gonna work. Wait represents the action of the philosopher to get a chopstick, while signal represents the putting down of the fork. Inside the do-while loop, we have a wait operation and signal operation. The modulo of 5 is there so that the semaphore index of the chopstick won't exceed to 5. So the next chopstick number for chopstick array of 5 is chopstick array of 1. If I is equal to 5, then I is plus 1. Then it is 6. So modulo of 5 is applied. The signal represents the putting down of the fork. Every philosopher will take adjacent numbered chopstick in the next adjacent numbered chopstick. So the process will prompt the philosopher to take its adjacent numbered chopstick. Next, it will take the next chopstick. Now, it will eat. Then it will put down the adjacent numbered chopstick in the chopstick that is next to it. But this solution has a problem. It can occur deadlock. It can occur when all philosopher will attempt to eat. So all of them will take adjacent numbered chopstick, but they can take the next chopstick since that chopstick is adjacent to another philosopher and is taken by him also. They will wait until that chopstick will be vacant, but it won't happen since the other philosopher won't drop the chopstick if he can't finish eating. They will wait and wait for a chopstick and nothing will be done. That's when the deadlock occur. How about we try using a third party? In this case, we have a waiter and round-robin and priority scheduling. Using this method will not make sure that all philosophers starts eating at the same time, rotates for equal attention, and if a philosopher's attempt to eat failed by the next turn, he will be prioritized so that the philosopher before him won't keep eating and eating, so that he won't starve. In this scenario, the first philosopher asks if he can eat. Since he has both fork available, of course he can successfully eat. In the next scenario, the second philosopher asks if he can eat. Since he has only one fork available, he fails to eat, so he puts down the fork. The waiter then marks him as a priority for the next rotation. In this slide, the third philosopher asks if he can eat. Since he has both fork, he can successfully eat. In the next scenario, the fourth philosopher is kept since he didn't ask to eat. Then, the fifth philosopher asks if he can eat. Since he has only one fork available, he fails to eat, so he puts down the fork. The waiter then marks him as a priority for the next rotation. Now, the first philosopher is done eating. In the next scenario, the second philosopher asks again if he can eat. Since he has only one fork available, he fails to eat, so he puts down the fork. He is not marked since he is marked already. Next, the third philosopher is done eating. In the next scenario, the fourth philosopher asks if he can eat. But then, the philosopher next to him, the fifth philosopher, is marked priority. He'll be able to eat first before the fourth philosopher. And when he asks if he can already eat, he only has one fork. So he failed to eat and will be marked priority for the next rotation. So in conclusion about this topic, a dining philosopher's problem is one of the classic issues in the operating systems. It can be described as 5 philosophers who want to eat. For example, there are 5 chopsticks on the table. So each philosopher must use 2 chopsticks if he would like to eat the spaghetti. If philosophers really hungry, then it will take 2 chopsticks, which is in the right and left hands. If there are philosophers who took 2 chopsticks, then there are philosophers who have to wait until the chopsticks are placed back. Inside this problem, there is the possibility of deadlock.